In this chapter, we will be working with conjugated systems to determine if a system is conjugated or not. First, we have to be able to determine if our atom that we are working with, whether it's a carbon, oxygen, or nitrogen, they have a p orbital. So when three or more p orbitals overlap, then in this case, we can call our system to be conjugated. So let's start with the simplest form of an alkene, which is ethylene. This is ethene as an IUPAC name and ethylene as a common name. And we want to know what is the hybridization of each one of these carbons in there, and how many p orbitals do each carbon have. So the first thing that you do, and again, this explanation is also applicable for oxygens and nitrogens. So you take the element in here. I do have two carbons. So taking one of them is more than enough. And whatever result I find for one carbon, that is going to be applicable for the second one. So carbon has an atomic number of 6. Go ahead and draw its electronic configuration. And then we know that the first shell is completely filled. The second shell here is partially filled. So this is why carbon has 4 electrons in its outermost shell, and carbon belongs to group number 4. Whether the bonds all they are single, they are double, or they are triple bonds. Carbon always makes 4 bonds. Carbons always prefer to be in its stable state, and the stable state is when the formal charge of the carbon is 0. It is 0 when it has 4 bonds in there. So when all the bonds around the carbon are single, then in this case, the hybridization of the carbon is going to be an sp3 hybridization, because you need 4 orbitals in there for the groups. So you need an s and the 3 p's. This is a total of 4 orbitals. When carbon makes double bonds, the hybridization is an sp2. And when carbon makes a triple bond, then the hybridization is going to be an sp. It is sp because carbon here only has 2 groups around it. So you need 2 orbitals, so this is why it is an sp. For this chapter, we're going to limit conjugation to systems with double bond. So systems with alkenes only and not alkynes. So let's go ahead and determine how many p orbitals we have for an alkene system. So we said over here that the outermost level is not completely filled, and this is the one that we're going to use in order to bond the carbon with adjacent atoms. So let's go ahead and draw the Lewis structure for ethylene to see exactly how many groups are there around each one of these carbons, and to determine how many p orbitals we have for each one of these carbons in there. So this is it. This is the Lewis structure in there. And we are going to consider the electronic configuration for each one of these carbons here. Just going to consider one, and then whatever I find for one is going to be the same for the other. So if we look at the valence shell, carbon has 2 electrons in the s and 2 electrons in the p. So let's go ahead and draw them. We have 2 electrons in the s and 2 electrons in the p. So in the s orbital, we do have 2 electrons. The p orbital is 3 subshells, px, py, and pz, and the p orbital has 2 electrons. This is a property for carbons, oxygens, and nitrogens. They do undergo excitation always. As you can see in here, we do have an empty p orbital. So this is going to make the atom unstable. So what carbon does over here is an excitation of 1 electron of the s orbital to the p orbital. So you are going to end up having your p orbital half filled, and the s orbital having one electron. So after the excitation, you always look at the number of groups around the atom. So over here, carbon has one, two, and three groups. So three groups, you need three orbitals. So for this carbon over here, you would need three orbitals in there. So this is why you combine them together, and this is called hybridization. So the hybridization for the carbon now is going to be an sp2 hybridization. It's a 1s and a 2p orbital. And then what you are going to be left with is the p orbital in there. When hybrid orbitals overlap with each other, then they make a sigma bond. When they overlap with a hydrogen, they make a sigma bond. So carbon here does have three sp2s because it does have three sigmas. It's a sigma here, it's a sigma here, and it's a sigma here. So the hybrid sp2 of the carbon overlaps with the s orbital of the hydrogen and makes a sigma bond. Same thing over here. Here, the hybrid sp2 carbon is going to overlap with the hybrid sp2 of this carbon over here and make a sigma bond. So whenever hybrid orbitals overlap, they make a sigma bond. Now for the pi bond. See the p orbital that is left here? Every single carbon is going to have a p orbital. So the p orbital here, when they overlap with each other, they are going to make a pi bond. Let's draw the valence shell representation for the p orbital in there. So I do have a p orbital on this carbon and a p orbital on this carbon. Notice that the p orbital here has one electron. So I will have one electron from this carbon and one electron from this carbon. These two are going to overlap with each other and they are going to make a pi bond. The capacity of the p orbital is a max of 2 electrons each. However, when the p orbital has one electron, it can overlap with another p orbital that has one electron, and this is when they make a pi bond. So pi bonds are restricted to p orbitals having one electron each. Here, because this carbon is an sp2 hybridization, we are left with a p orbital, a 1p orbital, and this is how we get our pi bond. We're not going to talk about the triple bonds. We're just going to limit ourselves to the pi bond. So every time you see an alkene, then the carbons of the alkene, both of them, each one is going to be an sp2 hybridization. And the system is going to be made up of 2 electrons. So every pi bond is a 2 electron in there. So let's say, for example, if I have a diene, then in this case, I know that every single carbon is an sp2 hybridization. So I'm going to end up having a p orbital here and a p orbital there. And then another p orbital here and a p orbital there. So now I'm going to end up having 4 p orbitals. And every 2 p's make 2 electrons because there is 1 electron in every p. So the system here has 4 pi electrons, meaning that 4 electrons belonging to the p orbital. This is how you determine the number of electrons in your system. Let's say, for example, now, if I have a carbocation, an allylic carbocation. So this is a primary allylic carbocation. Now I want to determine how many electrons I have. So I know both of these carbons are sp2 hybridization. So the double bond here is going to be a 2 electron. Now, what about this carbocation in there? Let's go ahead and determine the hybridization of the carbocation. So I know that carbon is positive whenever it has 3 bonds, right? So over here, it's going to have 2 hydrogens so that it can have 3 bonds, so it's a positive charge. To determine the hybridization, as we did before, go ahead and look at the number of groups around the plus charge. We have 3 groups, you need 3 orbitals. So the plus charge here is going to be an sp2 hybridization. So there's going to be an sp2 hybridization. As we said, every time you have an sp2, you are going to be left with a p orbital in this case. But the p orbital for this carbon is positive, meaning that it's empty. It doesn't have electrons. So if I draw the p orbitals for this structure, then it's going to look like that. I'm going to have a p orbital on this carbon that has 1 electron and a p orbital on this carbon that has 1 electron. These, they overlap with each other and make a pi bond, which is basically the double bond. And then on this carbon, I have 1 p orbital, and that p orbital is going to be empty. The reason why it's empty, because it is a positive charge. Going to be 3 p orbitals. And for the number of electrons in there, I only have 2 pi electrons, because I have a p orbital that has no electrons in there, and I have an electron in each of the p orbital. So I have 2 pi electron total for the primary allylic carbocation. Doing the same thing for the primary allylic radical. So if you have a primary allylic radical in there, and we want to know how many p orbitals we have, these 2 carbons are an sp2 hybridization. Now for a carbon that is a free radical, it needs to have 3 bonds. So if it needs to have 3 bonds, then in this case the hybridization is going to be an sp2 hybridization. sp2 hybridization means I have a p orbital in there. And I also have p orbitals for each one of these carbons. Each of the p orbitals for the double bond has 1 electron. And then for the free radical, it also has 1 electron. So this is the electron for the free radical in there. So in my system over here for the allylic, this is a primary allylic radical. It has 3 p orbitals, and it has 3 pi electrons, meaning that in each p orbital there is an electron. We're going to do the same thing for carbon ions, for allylic carbon ions. So this one over here is an allylic carb anion. Please review your formal charges. When a carbon is a negative charge, meaning that it has 3 bonds and a lone pair. So carbon here will have 2 hydrogens, so that it will have 3 bonds and have a negative charge. So the hybridization of this carbon is going to be an sp2 hybridization with a sigma bond here, and a sigma bond here for the carbon. So this is why it's an sp2 hybridization. Now for the lone pairs, they have to belong to the p orbital in there. So the p orbital for the carbon ion does not have 1 electron, it has 2 electrons in there. And then I do have a p orbital for each one of these sp2 hybrid carbons. So now if I want to draw the p orbital representation, then I will end up having 1 electron in each of these p orbitals. And for the carbon ion, I'm going to end up having 2 electrons in the p orbitals in there. So the total number of p orbitals is going to be 3 p orbitals. And the number of electrons is going to be 4 pi electrons. This is how many electrons they belong to the p orbital in there. So in these examples, I'm only considering my p orbital and how many electrons are there in the p orbital. If I have a system of 2 double bonds now, we've considered it before, then in this case, I'm going to end up having 4 p orbitals. So let's go ahead and draw these 4 p orbitals. And each of the p orbitals is going to have 1 electron, because remember, every sp2 hybridization will be left with 1 electron in there in the p orbital. So that these 2, they overlap with each other, they make a pi bond. These 2 overlap with each other and they make a pi bond as well. And my system has 4p orbitals and 4 pi electrons. So let's go ahead and define the term conjugation. Conjugation is whenever you have a system that has 3 or more p orbitals, and these p orbitals, they are placed on adjacent carbons. So here this one has 4 p orbitals adjacent to each other, so we say that this system is conjugated. Conjugated means that you do have a flow of electron where the p orbitals overlap with each other. So this is going to be your electron delocalization. This is where the electrons are going to hop from one p orbital to the other there. For the allylic carbocation, it's also a conjugated system because you do have 3p orbitals. This is the least that you can have. And these p orbitals, they are adjacent to each other. So again, you will have an overlap of the p orbitals in this case, and the system will be conjugated. Same thing for the allylic radical. The system is going to be conjugated as well, 3p orbitals on adjacent carbons. Meaning that for the system to be conjugated, all the carbons, they have to be an sp2 hybridization. They cannot be sp3, they cannot be sp. Okay? Same thing over here for the primary allylic carbocation. Again, I do have an overlap of the p orbitals. Now, even if the p orbital is empty, it doesn't matter because one electron can hop from one p orbital to the other, and this is going to be your conjugated part of the molecule in here. You highlight where the p orbitals are. If they are 3 or more adjacent to each other, that is going to be your conjugated part of the molecule. Because we have an electronic cloud and electrons can move from one p orbital to the other, conjugated systems, they do have resonance. So resonance is restricted to electrons being in the p orbital. If you don't have electrons in the p orbital, meaning that if you don't have sp2 hybridization carbons or atoms that are adjacent to each other, then you are not going to have resonance. So resonance is restricted only to systems that have p orbitals, where electrons, they can delocalize, meaning that they can hop from one p orbital to the other. In this chapter, we will consider allylic cations. This is the stability trend where it shows that allylic carbocations, they are more stable than the regular carbocations. Primary allylic is slightly less stable than secondary allylic than tertiary allylic. So if I want to compare the stability, all the allylic carbocations, they do form, and the reason why they form because of resonance, where electrons can move between p orbitals. So if I am looking at the p orbital for the primary allylic, I have a positive charge here, 2 electrons in there. Then I will do resonance, and now my positive charge is going to be on this p orbital, and these 2 p orbitals will have electrons. These two are considered to be resonance structure for the primary allylic. Both of them are equal in stability, and if you combine them both, you get the resonance hybrid.